Good day. For those of you who don't know us, we're the instructional staff for ECE 150, Professors Hiran Patel and Werner Dietl, and Douglas Harder. In this topic, we're going to look at libraries and calling functions. So in this topic, we will describe the concept of a library. Specifically, we will look at the C Math library. We will look at the global variables defined within that library, and we will also describe a function declaration, which allows us to call functions within a library. We will look at how we can call a function with specific arguments and understand how to use the return values. Specifically, again, looking at functions defined in the C Math library, such as the sine function, cosine function, the exponential function, and other functions such as ceiling and floor. We're going to look at a number of examples where we use the functions implemented in the C Math library. In our examples so far in this course, we have performed arithmetic, comparison, and logical operations, assignments, and we've looked at conditional statements and repetition statements, specifically for loops and while loops. Now, one question you should ask is, how can you use someone else's code? Do you have to author everything yourself? So, for example, suppose you are trying to simulate a system that is repeating, say, alternating current, or some sort of flywheel, or an internal combustion engine, and you require the use of trigonometric functions. How are we going to get the values of, say, sine of x or cosine of x? Now, recalling from secondary school, you learned about functions, and you knew that functions took arguments. So, for example, we have sine of x, where sine is a function that has an argument x. Similarly, there's the natural logarithm or ln of x, and we can take the GCD, or greatest common divisor, of two integers. So, for example, in secondary school, you may have calculated sine of pi over 6, ln of 3, or the GCD of 15 and 18. In secondary school, you would have described these functions as follows. The sine function takes a real value as an argument and returns a real value on the interval -1 to 1 inclusive. The natural logarithm takes a positive real value as an argument and returns a real value. And the GCD takes two integers as arguments and returns a positive integer. Now, in C++, a function is simply a body of instructions that allows you to specify certain parameters or values, and that function then, through executing instructions, calculates or returns a value based on those parameters. So, for example, there are C++ functions that calculate, for example, sine of x, ln of x, and the GCD of two integers. The purpose of functions is so that you don't have to reinvent the wheel. For example, someone else has already authored the trigonometric functions, so why do you have to write them again? Now, suppose you have authored a number of functions that either you or your friends or someone else may need to use. The solution for collecting related functions together for reuse is in C++ is called a library. Now, you've already used libraries before. If you need information on something, you go to an appropriate library, access a book, and that gives you the information you need. In C++, a library can be a collection of functions that you can call from your program, and we'll see how to do that. For example, if you wanted to call sine of x for a specific value of x, or calculate the natural logarithm of 3.5. A library can also have a number of global variables which have specific values that you can access. It can also include, among other things, objects and classes associated with object-oriented design. Now, we have not yet covered object-oriented design, so we will see this later on in this course. Now, at this point, we're just going to look at the C Math library. This is a collection of mathematical constants and functions. You can access the C Math library by including the preprocessor directive include C Math at the top of your program. As you may guess by now, another library that we have already been using is the IOStream library, or Input-Output Stream library. Now, first, in the C Math library, there are a number of global variables which you can now use as soon as you include C Math. For example, if you wanted to use the value of pi, you would simply refer to m_pi in all caps. You cannot use lowercase letters anywhere here, in which case that identifier will always evaluate to the value of pi, at least to the accuracy of a floating point number. You can now use these global variables in your program. Now, normally you should only have to actually include the library with the preprocessor include directive include CMath. However, there are problems with certain compilers, and so therefore some compilers require you to include the preprocessor define directive, where we define the symbol _use_math_defines. For the purpose of this course, don't worry about what this means. We will describe this later in this course. However, at this point, if you ever include the CMath library, just include this preprocessor define directive immediately before it. Now, we have a program here which we authored before. We query the user for the radius of a sphere, and we store whatever value the user gives us in a local variable radius. We then declare a local variable area, and we initialize it with the result of the calculation 4 times pi times the radius squared. Similarly, we declare a local variable volume and initialize it with the value 4/3 pi r cubed. Previously, we had a value 3.14 and changed assigned to a local variable we defined called pi. However, why always keep on cutting and pasting the value 3.14 and change when instead you can simply refer to m_pi, in which case you're always guaranteed the value is right and you did not accidentally copy the value of pi wrong. So if we run this program, enter the radius of a sphere, the user then types in a value and hits enter, and the result is displayed on the screen. The CMath library also contains a number of functions that you can use. Each function is described by the function declaration. So for example, the function declaration of the sine function is as follows: double sine, open parenthesis, double x, close parenthesis, together with a semicolon. What this says is that the sine function takes a single float as an argument, just like sine of x. The double to the left of the identifier sine indicates that this function returns a float. Now, the function that calculates x to the y is the function that has the name pow, and it takes two arguments. The two arguments are x and y, and both x and y are floating point numbers. The pow function then calculates the value x to the y, or more correctly, it approximates the value x to the y, and it returns a float. Now, if we had a GCD function, which the C Math library does not, then its function declaration would simply be int GCD, int m, int n. What this says is that if someone was to author a GCD, or greatest common divisor function, it would take two integers as arguments, and it would evaluate to or return an integer, specifically or hopefully that integer being the GCD of the two arguments that are passed to the GCD function. Now, the function declaration may also be described as the signature, prototype, or interface of the function. However, for the purpose of this course, we will consider this to be a function declaration. Now, you have already seen one function declaration in this course, specifically int main. What this says is that main, which you have already used, is simply a function that takes no arguments and it returns an integer value. Specifically, the only value that we have returned so far is 0. However, now we will return different values based on what the function is supposed to calculate and based on the values of arguments that are passed to the function. Some of the function declarations in the C Math library are for cosine, sine, tan, inverse cosine, inverse sine, inverse tangent, and an interesting one, atan 2, that takes not one but two arguments. Immediately notice, if you wanted to say determine the value of secant of x, there is no such function declaration, and therefore you must use 1 over cosine of x. Also is this interesting function arctangent 2. Arctangent 2 calculates the inverse of y over x, but takes into account the sine of both y and x. This allows, for example, x equaling the value of 0, or x being negative while y being positive or negative. Now, here's an example of calling functions. That is, we are calling the functions in the C Math library with an appropriate argument, or in other cases, arguments. So in this example, we query the user for a value of x. The user can enter whatever real value of x they wish, and we will then print out and calculate sine of x, whatever value of x the user passed. Because the sine function is in the standard library, we must prefix that identifier with std::, just like we always had to prefix cout, cin, and endlin with that same std::. Again, we will describe that later. Similarly, here we calculate cosine of x and the inverse tangent, or arctangent, of x. So if we were to compile and run this program, the program would query us for a real value x. We might type in 3.14 and then hit enter, and then this is what is printed to the screen. 3.14 is pretty close, but not exactly equal to pi, and therefore we see that sine of 3.14 is close to 0. Cosine of 3.14 is approximately -1, and arctangent of 3.14, which really has nothing to do with pi, is just the value that's presented there. Of course, these are only approximations, but reasonable. Now, in the previous example, we just called the functions and printed the results to the screen. However, in any arithmetic expression where you could have used a float or a local variable of type float, you can also use a call to a function that has a return type double. So, for example, in this first statement here, we declare y to be a local variable of type double, and we initialize it with a value of sine of x plus 1 for whatever value of x the user entered. Next, here y is assigned the value of sine called with the argument inverse sine or arc sine of the value x that was passed. So now the argument to sine is itself another function call. And that's okay, that also makes sense. Finally, we have this third assignment where y is assigned cosine of pi over 2 minus arc sine of x. Now, if you remember from secondary school, cosine of pi over 2 minus x is equal to sine of x, so therefore the second and third results should indeed be equal. So if we compile this program and execute it, it queries us for a value of x. Suppose we enter in 0.32 and hit enter. Then it tells us that sine of 0.32 plus 1 is approximately 1.31457 and change. Sine of arc sine of 0.32 is indeed equal to 0.32 as expected, and the third result also calculates to the same value. There are other functions in the standard C math library, including the hyperbolic functions, the exponential and logarithmic functions. However, whereas in calculus you refer to ln of x for the natural logarithm, in almost all math libraries, almost universally, the log function calculates the natural logarithm. If you wanted to calculate the common logarithm or logarithm base 10, the function is usually something of the form log 10. And so log 10 is a function that takes an argument x and returns log base 10 of that value of x. Now, other functions in the CMath library include the function we've already seen, pow, which takes two arguments, x and y, and calculates x raised to the power y, if defined. However, there's also the square root function and the cube root function. Now, calling square root of 3.2 is the same as calling pow 3.2 with an exponent of 0.5. However, the reason there is a separate function to calculate the square root is that the algorithm for calculating the square root of an argument is much faster than the more general algorithm that calculates x raised to the power y. The same is true for the cube root. Similarly, there is a function hypot which calculates the hypotenuse of a right-angled triangle which has sides length x and y. So essentially this calculates the square root of x squared plus y squared, but once again this is ever so slightly faster than performing the explicit calculation of calling the square root of x times x plus y times y. There are also other functions which you've seen previously. The ceiling function, or ceil, returns the least integer greater than or equal to the value of x, whereas the floor function returns the greatest integer less than or equal to x. Trunc removes the fractional part of x and returns that integer. Well, it actually doesn't return an integer, it returns a floating point number that represents the integer in question. Similarly, round takes the argument x and returns the integer that is closest to the argument x. Finally, of course, there's the absolute value function that simply returns the absolute value of the argument. Okay, here is a nice program that combines some of the ideas that we've already looked at, either in this topic or previous topics. First, we ask the user to enter two values, a and b, which we will assume define the endpoints of an interval. We will then ask the user, how many subintervals do you want? This, of course, will be some positive integer value. Now, if we have n subintervals, then that means we have n plus 1 equally spaced points. The distance between any two of these points is given by the formula b minus a over n. Now, a plus k times h, where k runs from 0 to n, therefore gives us the x value of each of these intermediate points, where when k is equal to 0, a plus 0 times h is a, and when k is equal to n, a plus n times h is equal to b, the other endpoint. We will now print out the point and the value of sign at that point for each of the n plus 1 equally spaced points. Therefore, if we were to compile and execute this program, suppose we entered as the endpoints 2.5 and 3.7 with 6 intervals. Well, 3.7 minus 2.5 is 1.2 over 6 is 0.2, and therefore the 7 points are 2.5, 2.7, so on all the way to 3.7. Together with these, we have the value of sign at those points printed to the screen. As you will notice, 3.14, which is pi, lies between 3.1 and 3.3, and sign for x less than pi is positive, and sign for x greater than pi is negative. An important takeaway from this topic is that if you are using a function that someone else has authored, all you really need to know to use that function is the function declaration, which tells you specifically how many and the types of the arguments, together with the type of the return value. Once you have both of these details, you can use the function in your program. However, you should also have a description of what the function is supposed to accomplish. For example, what are the units of the arguments, if any? What are the units of the returned value? What is the relationship between the arguments and the returned value? So, for example, the sine function takes an argument x and calculates the sine of x. Alternatively, you may have the GCD. It takes two arguments, that is, two integers, and calculates the greatest common divisor. Easy enough. Or you may have a more complex problem. Given a graph or a city map with vertices or intersections, given a starting vertex or intersection and a finishing vertex or intersection, find the shortest path from one intersection to another intersection. Now, if the actual behavior of the function does not match the description, this is known as a bug. That is, it's a situation where the expected returned value does not match the actual returned value. In this case, the person who authored the code has got to go back and correct the implementation of the function so that it does indeed return the correct value or the expected value. This may actually result in one of two changes. It may result in changes to the code, or it may result in a change to the description of what the function is supposed to accomplish. Perhaps indeed the bug reflects a situation where no solution exists, or no reasonable solution exists. So in the upcoming topics, we're actually going to look and see how we can implement our own functions in C++. And we will use functions to solve problems. Now, another cool thing about functions in libraries is, as long as you trust the author of the function, you really don't need to know how the function is implemented. You might not even care. You may never care how the sine function is implemented, nor may you care how the square root function is implemented. All you care about is the fact that it does do what it claims to do, and it does so with the required, in that case, precision. In most cases, you're not going to care, because it's not worth your time as a programmer to deal with how everything else is functioning. Your job is to solve one specific problem, and you will use libraries, that is, tools, to solve those problems, under the assumption that those tools are working. Now, as an engineer, you should still test to ensure that those tools are working as claimed, but your focus is the use of the tools, not necessarily the authoring thereof. Following this lesson, you now understand that C++ libraries contain global variables and functions, among other things. However, this is a start. Specifically, you now know how to look at a function declaration and understand how you can use the function declaration to know how to call a specific function, specifically by passing it the appropriate number of arguments of the appropriate type. You know that you can do something with the return value as you could do with any local variable or literal of the same type. You are aware of the CMath library and some of its contents. For example, the sine function, the arctangent function, etc. You also know now that you can use a function without actually understanding how it was implemented. You don't have to know how any of these functions were implemented. How is the square root function implemented, or how is the square root even calculated? In the next topic, we will actually see how you yourself can author a function in C++ so that you and possibly someone else can call that function to accomplish goals that you require to be performed. Normally I just say here are the references. However, this is a very important reference. C++.com has a comprehensive reference of all the various libraries. So if you want to see all of the functions that are available in the CMath library, then visit this website and browse through some of the functions. In each case, you will, if you select a function, you will see the function declaration and a description of what that function is supposed to accomplish. Here's the acknowledgments, the colophon, and a disclaimer. Cheers!